Uh, Good evening, everyone. Myself Subhrangshu Shekhar Jaina. I am from Baleshwar, Odisha. So I welcome you to the discussions of the topic, which is from inorganic chemistry. The chapter name is coordination compounds, and in that coordination compound, we will be specifically discussing about that one part, one chapter, one topic known as crystal field theory. Okay. The topic name is our topic name of discussion is crystal field theory, shortly also known as crystal field theory. So first of all, before moving ahead, we should know what are the features of crystal field theory and what are the assumptions of crystal field theory. Before that, why first question we should know, that is why crystal field theory or CFT. Earlier, before CFT, we had the explanation of theory explanation, that is VBT. But what happened with VBT is VBT could not explain correctly of the characteristics behavior of few examples. That was it could not explain it couldn't explain the characteristics of few iron compounds. So that's where the need of CFT comes into the picture. Okay, so that's why we're discussing the CFT today. So what are the features of crystal field theory and how it proceeds? So in the crystal field theory, one point, the most important point is the CFT. CFT considers the metal and ligands as point charges. Okay, CFT considers metal ligand as point charges, and the formation of compound through CFT happens through formation of ionic lattice. Okay, formation of compounds proceed is the formation of ionic crystal. Okay, so I'm mentioning here how this ionic crystal forms. A brief introduction I will give you of formation of ionic crystal. Formation of ionic crystal, how it happens actually. In the formation in the ionic crystal, the anions create the lattice. Anions create the lattice, and inside the lattice one void will be present. Okay, and that cation will sit in that void. So I can clearly say that in the if we will discuss in the one line, we can say ionic lattice are those formed by anions. A lattice formed by anions, and that cation will stay in the void formed by the anions. Okay. So how can we relate that statement to here in the CFT? The CFT, the metal and ligands are there. Metals known as positive charge, uh, ligands will be having negative charge. Okay, and I mentioned that these are known as point charges. That means there will be some ionic interactions. Okay, the ionic interactions, and in the CFT, this metal are known as stationary charge. Okay, metal is known as stationary charge, and this ligand known as moving charge. Basically, I am discussing how this CFT splitting and all we are moving ahead. We will come to that point actually. How that happens. So, uh, if I conclude this slide, it will be what it will be. It is that CFT consider the metal ligand as point charges, and the bonding between them is purely electrostatic in nature, or you can say ionic in nature. Okay, so in the next we'll be discussing how this bonding and then formation of happens. Okay, so I'll be clearing this in 1, 2 and 3 seconds. Thank you. Okay, so now we discuss that these are termed as considered as point charges. Okay, so you can say, let's say my metal is in here. Okay, now a ligand that is having a negative charge is stays at infinite distance. Okay, is at infinite distance. Now this ligand will approach the metal due to the electrostatic force of attractions. Okay, so the interaction due to which the ligand approaches the metal, it is known as primary interaction. Primary interaction. Okay, so now in the next case, let's suppose this metal is near to this is how much the ligand can approach the metal. This is the shortest distance between the metal and ligand, let's say. Now why cannot ligand enter more closer to the metal? Because if it go more closer, that metal itself has some vacant orbital, no? Those are also negative in nature. Okay, so now this negative and negative, so now this negative will repel each other. So this interaction known as secondary interaction. Secondary interactions. Okay, so in crystal field theory, two types of interactions are there. One is primary interaction, another one is secondary interactions. Okay, so this actually applies when the ligand stays far from the metal. You can say this is a far field, this is a near field. Okay, so in this we have discussed about the two interactions which are generally discussed in the CFT. Now we'll be moving towards the formation of octahedral complex with the help of CFT. With this help of two interactions, we'll be discussing how this formation of octahedral complex forms. Okay, so I'll clear this in 3 seconds. 1, 2 and 3. Thank you. Okay, so now we'll discuss formation of octahedral complex. Okay, thank you. So we know that in octahedral complex generally 6 ligands are there. Okay, so now I want you to imagine a cube. Okay, 1 minute, I will draw the cube, then I will explain it. Okay, so now just suppose this our metal is at center. Okay, our metal is at center, and that orbitals, the metal vacant d orbitals are there. In the out of the 5 orbitals, there are two. There is classified as some that out of them some classified as axial orbital, and some of them classified as non-axial orbital. So those axial orbital actually pointed towards the face of the cube. Okay, and these axial orbital are pointed towards the face of the cube. So now for the formation of octahedral complex, these ligands approaches through facial manner. Facial manner means these ligands will enter through the face of the cube. Okay, so now if the ligand enters through the face of the cube, and in the face and towards the face, the orbitals which are directed, those are known as axial orbital. Okay, so now the ligand comes to the face of that cube, but ultimately it goes and overlap with that axial orbital, because the axial orbital was directed towards the face center of that cube. So that's why we also say that the formation of octahedral complex is happens through a axial manner of overlapping. So this is the reason why called for the formation of octahedral complex. We tell that this is the axial manner of overlapping. Okay. So now what will happen? Okay, this ligand will approach from the far field, let's say infinite distance. This will come towards metal due to the positive charge of Fj, and we can say the Z effective or effective nuclear charge due to the nuclear force from the metal that expressed by ligand, and the ligand approaches the metal. Okay, this is our primary interaction. These are primary this is our primary interaction. Okay, what is primary interaction? I already discussed. I will say again here. Primary interaction is that interaction when the ligand stays far away from the metal and approaches towards the metal due to the nuclear force of attraction experienced by the ligand from the metal. Okay, so this is primary interaction. Then when 1 minute. Okay, now when this ligand approaches near field, let's say now the ligand approaches near to the, and I will copy this picture and explain it. Okay, now imagine our ligand is near to the metal. Okay, this is that distance this ligand can approach. This is the shortest this is the shortest distance between the ligand and the metal. Okay, so now this ligand cannot enter more towards the vicinity of metal. Why? Because if enters more towards this metal, then it will experience the repulsion from the metal orbital. I will write the experience repulsion from the orbitals of metal. Okay, and this is known as secondary interaction. Okay, I hope all this is clear to you. And the next we'll be discussing what happens with when the interactions occur. Okay, so I'll clear in the second 1, 2 and 3. Thank you. Okay, so now we'll be discussing the consequences of these two interactions. Okay, let's say first we are having primary interaction. What we saw the primary interaction, the primary interactions, the force of attraction experienced by ligands. Okay, now you say me when this force of attraction was expressed by ligands. Okay, due to the force of attraction, ligand will approach towards the metal. Okay, and due to that metal, due to the approach of ligand towards the metal, the orbital of metal, all the d orbitals of metal will experience some energies. Okay, so now since this is come from far field, all the d orbital, okay, 1 2 3 4 5, all the d orbital 1 2 3 1 4. Okay, so when this ligand approaches from far towards the metal, all the d orbitals experience a same amount of repulsions. Okay, so 1 2 3 4 5. So due to this an excitation of happens, you can say this is our energy profile. So due to the primary interaction, all the d orbitals experience same type of repulsion, and due to that repulsion the energy of the all d orbital increases equally in manner. This is known as primary interaction. This is the consequence of primary interaction. Now what happens? Now we'll discuss the consequence of secondary interaction. Now tell me, when the secondary interactions was happening, which type of orbital was experiencing more repulsion from the ligands? It is axial or non-axial? Axial or non-axial? The answer will be it is the axial ligand. Why? Because that ligand were approaching the cube, through the face, and along the face axial ligands were there. That's why the axial ligand experience more repulsion when the ligand approaches nearer to the metal vicinity, metal cloud surface. So due to the secondary interactions or splitting occurs, you can say that axial ligand will experience more repulsion. That's why in order to counterbalance, we can say the non-axial ligand will happen this one. So this is the splitting of octahedral due to CFT. Okay. Now this energy difference between this one is known as del O. This is known as crystal field splitting energy. Crystal field splitting energy. Okay. I hope the splitting of octahedral complex is clear. Now we'll be discussing some examples based on these octahedral things. Okay, so I'll clear these things 1 2 and 3. Okay, so now we will be calculating the crystal field stabilization energy. Calculation of CFSE. Let's say now consider an example: manganese H2O whole 6 plus 2. Okay, plus 2 means the oxidation state is plus 2. Okay, so scandium, titanium, barnate. So in the plus 2, the configuration of manganese will be 3d5 4s0. 3d5 4s0. Let's make it plus 3. 1 minute. We'll make it not plus 2, we'll take it as plus 3. It will be better to take example. So if it is plus 3 means it will be d4. It will be d4. So now this how the splitting happens: 1 2 3 4 5. So the axial orbital will have more repulsion, so that will be of more energy. This is our barycenter. This is our barycenter. Okay, so now since these 2 orbital are upper in energy and these 3 orbital are down in energy, okay, so we can say I will separate this 2 energy. Okay, so this will, each orbital will get 3 by 5 del O. Since it is a minus, it will get as each orbital is 2 by 5 del O. So here it is d4, so we will fill d4 orbital 1 2 3 4. So how it will be filled? This is weak field ligand, so single field 1 2 3 and 4. Okay, now if you calculate the CFSE, how much energy will be, it will be. Okay, so now here 1 electron in the upper orbital will into 3 by 5 del O plus 3 into minus 2 by 5 del O. It will become 3 by 5 del O here minus 6 by 5 del O. So the answer will be minus 3 by 5 del O. Okay, so this is our CFSE. These are CFSE. Okay, so we'll discuss one question that one came in that previous year of NEET. So the question will be in the next slide I'm discussing. Okay, here few questions are come like compare the wavelength. Compare the wavelength. Let's say there are two example. One is a cobalt CN6 3 minus or cobalt Cl6 3 minus, and question is compare the wavelength. Compare the wavelength. So how to solve this question actually? So you can do this with the help of crystal field theory. So you know that crystal fields theory, it is how it looks like crystal field theory. 1 2 3 4 5 1 2 1 2 3. Okay, so this distance, the separation is known as crystal field splitting energy. So that is also energy, no? So here asking to compare the wavelength. So we know that how the relation, we know the relation between the energy and the wavelength, that is inversely proportional. Okay, so now in order to compare the wavelength, first we don't have directly the values of wavelengths, but we have that we can compare the energies between them. From the energy comparison we will get the answer of wavelength comparison. Okay, so now we'll discuss two examples. One is cobalt Cn6 3 minus. Here the ligands are Cn minus, that is strong ligand. Okay, strong ligand means more splitting in nature. In the second case, cobalt Cl6 3 minus. Here the ligand is Cl minus, that is weak ligand. So weak ligand means that splitting. In this case, this splitting, in this case the splitting, you can see the splitting is more for the cyanide complex, but this one is less for Cl complex. So if you compare this del O of Cn and del O of Cl, which will be more? This will be more. So now if they compare the wavelength of these two, will be inverse of this one. So if they ask compare the wavelength of which of the wavelength is more, so our answer will be the chloride complex having 3 minus is of will be having high wavelength. Okay, I hope understood the question, and we will be discussing a next question. Okay, sometimes they also ask the magnetic behavior. Okay, magnetic behavior and magnetic behavior. So I will not discuss that directly. I will draw a diagram, that on in that diagram a tabular form. In that table we will be discussing all things. Let's say now I consider a example of FeH2O whole 6 plus 2. Okay, so now if it is plus 2, the configuration of metal will be 3d6 4s0, 3d6 4s0. Okay, so this is the d electron configuration. I will write one by one. So the the configuration is 3d6 4s0. Now this ligand is strong ligand or weak ligand? This ligand is weak ligand. Okay, so now if it is weak ligand, let's discuss about what will be the hybridization of this one. Hybridization of this one. If this is strong weak ligand, if this is weak ligand, then that will be 1 2 3 4. Okay, 1 2 3 4, 1 2 3 4 5 6. See, in that lower orbital there is no, in the inner d orbital no vacant orbital is there, and since it is weak ligand, it cannot pair up also. So in order to form this complex, so it have to take the outer d orbital complex. So that is known, that will be of sp3d2, known as outer orbital complex. Okay, I hope this is clear now. So hybridization will be sp3d2. Now OOC or IOC means, OOC means outer orbital complex, IOC means inner orbital complex. So this is our outer orbital complex. Okay, now we can say, if they ask about magnetic behavior, now say me, this will be paramagnetic or diamagnetic. See, there are presence of unpaired electron is there. So how to know paramagnetic or diamagnetic? So if they ask you, how will you know? When the compound is paramagnetic, it will be of, paramagnetic means presence of unpaired electrons. If the diamagnetic means absence of unpaired electrons. So now tell me, this complex will be paramagnetic or diamagnetic? We can clearly see that there is a presence of unpaired electron, hence it will be paramagnetic. Okay, so I'll clear all the things now. 1 minute. Before clearing, we'll discuss one more thing also. What will be the spin value, total spin value? What will be the spin magnetic moment? What will be the spin magnetic moment, mu? The formula is n into n plus 2 root over Bose magnetron. Here n means number of unpaired electrons, Okay, so in this complex, number of unpaired electrons are 1 2 3 and 4. So the spin magnetic momentum will be 4 into 6 root over, that will be 24 Bohr magnetron. Okay, so few more things we'll be discussing here. I will first clear this. Okay, so now we'll discuss what are the splitting pattern for this complex, iron complex. Okay, now we can discuss that this compound is weak ligand. So 1 2 3 4 5, 1 2 3 4 5 6. Okay, 1 2 1 2 3, 1 2 3 4 5 6. Okay, so this is that splitter diagram for the CFSE, crystal field diagram. So if I ask you, and these lower orbitals are known as T2G, this higher orbital known as EG. So if I ask what is the splitter state configuration, it will be T2G4 EG2, T2G4 EG2. So this difference is known as del O. So now if I ask to, if we need to calculate the CFSE value for this complex, how can we calculate? First we will calculate this one. So this upper orbitals will get 3 by 5 del O. This lower orbital will get 2 by 5 del O. Okay, and this is our barycenter. So now how to calculate this CFSE? CFSE will be 2 electrons in the upper orbital, that is 2 into 3 by 5 del O plus 4 into minus 2 by 5 del O. This will become 6 by 5 del O plus minus of 8 by 5 del O. Finally it will become minus 2 by 5 del O. Now if we are given with this delta O values, let's say for the example I'm asking, it is saying del O is 100 centimeter, then it will become minus 2 by 5 into 100, 20 minus 40 centimeter inverse. Okay, so this all the things I concluded in that one slide. Okay, now we'll discuss one more question that was asked, that a neat question, previous year question. Just tell me this one, titanium H2O all 3, this one complex is your paramagnetic or diamagnetic. So we know that scandium titanium, it is be of 3D2 4s2. Now oxidation state plus 3 means it will be 3D1 4s0. We can see that in the d orbital 1 2 3 4, and this one 4s. So we can see here presence of one unpaired electron is there, presence of unpaired electron, that means it will be of paramagnetic. Okay, I hope it's clear to you now. I have discussed few questions from the CFT part and discuss how CFT works, the splitting of octahedral in this lecture, and thank you.